Is it working? Yeah. Okay. Cool. Okay, I think we can start, right? So welcome back, everyone. Yeah, to our third session of this course. If you have been checking out our website since the weekend, you might have seen that there was some changes, some significant changes, and I'm perhaps very quickly explaining these changes, how they are motivated and what they are. So we have a little bit restructured the courses into actually 3 categories, right? So there is like the course, we understand the course now in this direction. This is the course, here. And there is some basic lectures in the very beginning, or actually we try to push them almost there where you need it, but it's more, of course, of these lectures in the beginning, yeah. And there is some lectures that you already know. This is, for example, how to set up your coding. There will be another one coming about 101 of microbiology. What is translation? What is transcription? Because we got this feedback that this is, of course, not known to everyone who starts this topic. About what is the differential equations. I mean, you have seen them, but like we are providing this a bit post-mortem, let's see. And so this is marked as background material. Then there is the normal lectures with the date. Like we had it, for example, introduction lecture, or Thomas, the chemical reaction network lecture. And then there is something which is called advanced topics, which we are actually having one today, right? And the advanced topics, they are understood like as branches from this course here, right? So the idea is this is not something that's completely aligned with a mainstream computational bioengineering course, yeah, what we think you should really know as a computational bioengineer. This is much more if you're interested to go in a certain direction, to branch into depth, actually, to have a real focus on this topic, normally on the topic that we had just before. Yeah? So in this case, it will be an advanced topic on, let's say here, chemical reaction networks in a very particular setting, which you will see in a second. Which is distributed algorithms, how to use them in distributed algorithms. So we are doing an exception in actually talking about such an advanced topic in live today. Normally, these advanced topics are read-only, right? Like these basic things, they're read-only. We will not have a course on this, but you can just look it up whenever you think, oh, this is interesting for me, or oh, I don't know the basics about this. Feel free to check it out, and we will announce when there's new courses coming like this. Okay, so there is also some. If you check out here the later lectures, there is some new topics that are popping up, because we have now completely designed the course. And what are these topics? So some of the topics are actually from a wish list. When you registered online, we ask you to state some wishes, what you want this lecture to be about, and we try to fulfill these wishes as good as we can. And the second thing we want to do is here, this lecture will have actually a topic, or let's say a running example, right? And this running example will be to build an inverter, a genetic circuit as an inverter. So what's an inverter? So it has some input, it has some output, right? And let's say a purely binary inverter would be just, if you feed it a 0, it should output a 1, and if you feed it a 1, it should output a 0, right? This is the classical binary inverter, which you probably know. And we want to implement this as a genetic circuit. That's a very simple circuit, but you will see it has all these different things. It touches all these topics here. So we think this is really a nice running example to get started in this topic. And it's more complex than one might think. Okay, are there any questions to the rearrangement so far? Like this is, yeah. Perhaps Perhaps one thing to say is also the homeworks and the problem sessions. Like now that we have kind of finished the introductory part of the lecture, they will more and more go towards this running example now. So this is really the running example now, and then everything will focus in this direction and explore this a bit more. Okay, I think Quick reminder, next week, the home exercise is due. Please don't forget to, please don't forget to send it to us. If you want that, we take a look at it, of course. I mean, for those in present, it's not a want, it's a must. But for those online, of course, if you want to that we take a look at it, send it to us now. Okay. If there is no more questions, I think I start with the lecture part. Here it is. Okay. So okay, so let's get back to what we really want to do, and this is to build circuits, right? Genetic circuits. So there is actually many different ways, and there will be a different lecture just on the topic circuits and gates, actually 2 lectures. So this is very brief recap just for you to have an overview. There is different ways to build circuits. For example, such an inverter here, right? You can use different pathways, like biological pathways, to instantiate these components here to create this biological circuit. And one way is like to use molecules. So in this case, your input would be some concentration of a certain signaling molecule or protein or some metabolite, whatever is sensed by this circuit. And your output could be also a concentration of, for example, GFP or something. So another protein, an output protein. But there is different. So you would. This is what we have seen so far. Kind of when we had, for example, the repressor repressing some promoter here, and here having our GFP, right? That is the output of the circuit. But you can also implement this in different ways. You can use, for example, the CRISPR machinery with DCAS9 and things for those who know this. So this is a very nicely targeted thing to target exactly these subsequences here to much more targetedly and systematically repress certain promoters. That's also completely fine. And there's many techniques, like flip bases and so on. And a very nice overview. We will not do this overview here, but just click on this link and check out this paper. This is a really nice overview if you want to get a brief introduction at what technologies exist. And it's while it's a little bit an older paper, I mean it's already 10 years, it still captures very nicely the landscape. So it's still a very good start. But there's of course a problem. Like when you really want to go big, and we will not do this in the course, of course. Like, I mean, as I said, the example will be really just one inverter, and this is already complex enough, But if you think of, let's put several inverters here, I don't know, and let's combine this with an OR gate, and let's do some feedback with an AND gate here, and so on, and get more and more complex. I mean, you easily get complex when you want to implement an ALU or a little microprocessor or whatever. Even very small things already have really hundreds of gates. Even very simple functionality, like a multiply and add or something. So how to get this into a cell? And the answer at the moment is it cannot at the moment. So we don't have the technology to do that. So research is about like at 10-ish, 11 gates to put in a single cell and a bacterial host. So one principal idea that research is exploring is actually to distribute this among different cells, right? Like for example, in your human body, you can also not expect that a single cell of your human body does all the jobs. This is not going to work. There is a lot of specialization, a lot of organization, and they are cooperating to solve the common goal to keep you alive. So why not do that with a bacterial colony, right? I mean, this is not forming a tissue a priori, unless you engineer it perhaps to do that. But still, you can think of distributing it and communicating between the different cells. And this is this is a very, we think so, like coming from the discipline of distributed computing, we think this is a very interesting approach. I mean, this is not yet a solution. It's an interesting approach right there. And we wanted to fascinate you a little bit about distributed computing in this lecture. So what we thought of is just to give you a very brief recap about what is actually distributed computing. And okay, how to do that like in 5 minutes? The idea is distributed computing is about like you have computational nodes, right? And each of these nodes is kind of a local computational unit that can run local jobs, yeah? And it's trying to communicate with the others by, for example, by sending and receiving messages or writing to a common storage, yeah? It is actually communicating with the others to solve a common global problem. Yeah? And why would you want to do that? I mean, sometimes it's like in the E. coli case. Sometimes it's just too big a computation to run on all. Sometimes you have very beautiful, nice local algorithms where it's actually much simpler to think of a little local computation than to solve the big global computation itself. Sometimes you do it for resilience, because if it's a big global thing, it can easily fail, right? Or it doesn't scale at all. So there is many different reasons to go distributed. And perhaps the big two directions in distributed computing, as it's done in computer science, is like to consider static architectures on the one side, yeah? Or to consider dynamic architectures on the other side. That means, for example, this network could be completely a static network. For example, we just built this network, and this is our distributed system, right? For example, this would be done if you, let's say you're designing a distributed system for a bank, yeah, that needs to run transactions in a distributed way, yeah, because they want to be resilient. They don't want, for example, that if the cluster in London crashes or is attacked, yeah, that everything is lost for this bank. So they want to go distributed, but you really engineer this in a very clean way that you have, for example, a connection from, I don't know, from here to here. On the other side, there is very dynamic architectures. For example, you can think of these being people who communicate in a social network. And the people would, for example, talk to different people over time. They would change their contacts and they would add friends. They would perhaps lose friends and so on. So this is a very dynamic distributed system. Yeah? And you could be interested in questions, for example, how do opinion waves propagate in this network? Yeah? How is an opinion formed by such a distributed network? Yeah? So this perhaps very quickly there is huge bodies of research about this, but this is very quickly the kind of, on the one side, fixed architectures, and the other, the dynamic architectures. And we of course, with our E. coli, since we are not going in the direction of tissue engineering or something, we are much more looking at the dynamic architectures. So we are really, like in our sense, the E. coli will probably be in a liquid mixed culture, and it will probably communicate whatever this means. We will see this in a second. Well, not in a second, but in 10 minutes. It will always communicate to new bacteria. Yeah? Okay, I'd like to, this is a bit of a thought experiment, and we think it's a nice experiment to get used a bit to distributed computing, and we will see this will go in a direction. Yeah? At the moment, it's not motivated, so don't think about why we want to solve that problem, but look at this picture. So that picture is a very simple Python script that's drawing 100 little balls in a 2D space, so circles, and they have two colors. Yeah? So there is actually, I mean, I don't want you to do the count, but there's actually 51 of one type, of one color, and 49 of another type. Yeah? And the question I want to answer you or to think about is like, how would we determine who is actually the majority here? I mean, we can have, of course, some extra rule. If we say they're exactly 50-50, then let's say the rule is you can tell me any color, yeah? But in case there is a majority, you should really tell me the majority color. Yeah? And I mean, okay, what an algorithm, I mean, not a computational algorithm, but let's say a social human algorithm would be just start here at the top left, right, and count. So keep two lists of counters and just count, and in the end tell me what is the bigger number. Yeah? But that's a very tedious algorithm. I mean, already it's not fun here, right? It's definitely not fun here. It's the same example. The difference is again 2. I mean, we see this doesn't scale. There is no way this goes anywhere like us counting these numbers. And I would be the first probably, when I'm here, I would lose the line and just have to start all over again. So it goes nowhere. Yeah? So can we do something distributed here? And let's make the game, let's say, perhaps even more difficult. Yeah? Let's say it's not only a picture, but this is actually moving balls. Yeah? This is molecules. I mean, now try to count them. And I think now it's game over. Yeah? Like there's no way you can keep track of all these balls. Yeah? There is a surprisingly extremely simple algorithm that does that. If it's distributed, like it's not like you would be the centralized person trying to count that, right? But if it's distributed, there is a very simple solution. And of course, before I say what is the solution, we have to define the rules of the game. Yeah? Like what is an allowed solution? Yeah. And this is very typical to computer science. Like whenever you try to, there is always the problem. Then you have to think about what is the rules of the game. Like what is actually an algorithm in your system? What is allowed? What are allowed steps for you? And then you can think of a solution. Yeah? And let's say what we allow here to be distributed. I mean, what means distributed? Distributed means something. It should be something local. Yeah. It should, like every ball should be interpreted as a computational unit itself, and it should only do something very, very local. And the most local thing you can do is actually only do something if you bump into another ball. Yeah, I mean that's super local. Yeah? You see only exactly your little neighborhood around you and a little epsilon more. Yeah, yeah, and what could this rule be? So this rule could be, for example, I mean let's call the one color A and the other color B. This rule could be actually if both balls of different color A and B bump into each other, they are both vanishing. Yeah. This is a way. I mean, we have of course to explain that this is a valid rule to vanish. Yeah. There might be systems where it's not allowed to vanish. Yeah. But for example, if you're not allowed to vanish, you could think of I'm going to a particular state, which is I don't know, a gray color, which doesn't interfere in the system anymore and doesn't do anything. I behave like a neutral element anymore. Yeah? But here, let's say we allow that you just vanish. Yeah? That's simpler even. Yeah? And I mean, we know this rule, right? We kind of know that A, B bumping into together and both vanishing. Actually, that's a chemical reaction network. Yeah? So that would be just a chemical reaction. A plus B gives nothing. Yeah? Right? We don't care about rates here. We assume any constant rate constant. We don't care here about this for the moment. But what we assume is actually mass action kinetics. So that the total rate would be a product of AB times some constant. So there's 2 points made here. First, actually chemical reactions are kind of distributed algorithms, right? And they can actually solve useful problems. So let's do that. Let's just run it. Oops, wrong directory. So what I prepared here is actually a little code that has around 700 lines of code. So it's not too big. And you can just initialize how big this volume will be, like 400 times 400 pixels. You can initialize with A has 51 and B has 49, for example, exactly like the instance we have seen before. And then the reactions, for example, AB goes to none, none, so AB goes to nothing. Yeah? So you define the chemical reactions, and then you can just run it. it's using, by the way, if you're just for fun, if you're interested, it's implementing a Pi game. So there's a Pi game library where you can code some little games, and this is exactly perfect to show this. So let's do that. And that's it. That's our game running. I hope it works. There is no bug now here. Yeah. So 2 remain, yeah? We started it with 51 versus 49. Right? And two remain. And 2 remain actually of this species, yeah? So we have here 2 in the end, and here 0 in the end, right? And that's an interesting graph. I thought that would be fun to plot. Yeah? So here you see the time in seconds. Yeah. So that's I think I'm not sure if it's real time seconds, if it was 7 seconds so long. Yeah. But let's call it seconds. Yeah. And here is the particle counts, and you see the 2 different species. They started off with 51 and 49. Yeah. And they went here to 0 and 2. Right. So a question to you, do you see why this algorithm works? Like, is it clear to you that it does work, that it really returns the majority? And by the way, we have to specify what it means to return the majority. Like in our case, that would be only the majority persists. So the answer the algorithm returns is the species that persists. Is that clear why it does that job? Okay, great. Yeah, so the big observation is actually to see that the difference is actually maintained. Yeah? Whenever you collide A plus B, it's removing 1 from both. So it never touches the delta, right? And the only thing you have to prove is now that 1 actually dies out, and then the proof is done, right? So, and you saw that was an amazingly simple algorithm that solved an amazingly complex problem. Yeah? So that's really cool for this, like what we thought. Okay, so then the next thing you might observe here is actually that's really fast, right? I mean, it goes from 50 to 0. I mean, okay, it goes very fast to 5, right? And then it takes forever. But that's okay-ish, probably. Yeah? But the beginning is really, really fast. So let's get back to our lecture. Yeah, there is just to mention perhaps 3 techniques how to prove that, or how to get confidence that this algorithm does the right job, right? So the first thing is actually you could run this particle collider many times and be confident that it does the job, right? That's what I just did 1 time. You could trust it after once or not. Yeah? There is a second approach, of course. If you paid attention to the last lecture, you know that you don't have to run this particle collider. This particle collider was like tons of code, and it was essentially simulating Newtonian physics. Yeah? I mean, a simple Newtonian physics, but it was a physical simulator. You could just say, why should I simulate physics? I paid attention to Thomas' lecture. It's actually behaving like a CRN. So it's a completely well mixed. I don't have to simulate any physics. It's just exponential distributions that I'm drawing. And you can totally do that. And this is what we did here. We did this in MobSpy. And this is what you get. And it looks completely the same. I mean, of course, the random generated draw different numbers here. So it's not the same, but you can be convinced that it's really doing the same. And now you have speed up your process incredibly, right? Like my previous simulation took, I don't know, 20 seconds to run 1 time. MobSpy, I mean, it takes probably milliseconds or something to run the simulation. So you've incredibly speed up already your simulation. Yeah? But you can speed up it even more. And this is not always possible, but sometimes. And this is why we try to teach it sometimes. You can use math, and suddenly your simulation takes 0 seconds. Because you just show for all simulation that something holds. Right? And here I gave you the argument, or you actually knew the argument already, like, actually it's a clever idea to look at the difference and see that this is an invariant, a constant. And then just showing This just takes a bit time, but it's doable. And you will do this in the problem session, yeah, as a, I think, second exercise, to show that this algorithm is so incredibly fast that it has constant runtime, like big O of 1 runtime complexity. Yeah? But that's very untypical for algorithms, but it's really, really cool. So that means, of course, now you would have to ask me, what's the parameter of this? And the parameter here would be the minimum number. So the B in our case, the 49, this would be the asymptotic parameter, but it's constant in the minimum. Yeah, by the way, like this reminds me, there is one basic course already online about asymptotics, like big O notation, omega, and so on. Yeah, and there's one already online about MobSpy. Yeah, so you can check both out. Yeah. Like, give me just a second. But if there is questions, like, feel free, of course, to post them or text it. So there is a second discipline which we kind of like a lot, and this is robust circuit design or circuit design. So I mean, this comes, of course, like classically, this comes of circuits in silicon, right? You build some chips, and there is very interesting ways how to build robust circuits for such chips. And this has tons of application. You can just think of, for example, circuits that have to live in environments where it's very likely to have ionizing particles. For example, that's very high up in the air, right, or in the space. Right? That would be the case. But it's also true actually for cars. Yeah, if your car is driving up like a mountain, and there's many cars, like if you sell a car, like you easily have millions of the same product, right, and they drive up mountains, they're actually more likely to hit by ionizing particles and so on. So you really care for such things, also in consumer products. And there's very interesting things how to make this more robust. And typically this is technology changes, like you build, for example, in bigger technologies, you can do that also algorithmically. And one thing to do that is actually doing it by signaling. So like a normal bit that you want to communicate in a circuit, let's say you want to communicate from here to here. Just this is the communication line. Yeah. You encode that by a single wire, right? Going between some lower voltage in this area and some higher voltage in this area. Yeah. So for example, let's say this is going from 0 to 0.3 volt, and this is from 0.7 to 1 volt. So you encode this actually by two different nicely separated voltage ranges. That's okay, but for example, if you're hitting here by an ionizing particle or any kind of noise here will disturb your signal. Yeah, and it has some other drawbacks. Yeah, for example, you cannot in this logic encode that you're still waiting for an input. Yeah? Right? There is like whatever you receive, it could be already a signal, so you have to compute something. You cannot say you don't have yet an input, right? There is a very fun way to signal. This is actually dual rail encoding. Yeah? So you use actually a 0 line and you use a 1 line. And now you just make a pulse, let's say on the 0 line, and you don't do anything on the 1 line. Yeah? And that is signaling actually a 0 here. Yeah? What you would do like for the next one is like there's different ways how to do that. If you go back to 0 or if you just each transition is actually a signal or something. But here this has several nice properties, right? So first you have really dedicated lines for these logical levels. So that means you can be much more noise robust here. For example, if you have an ionizing particle and you make the two lines very close to each other, that's actually hitting both. Yeah? So the difference stays untouched by this, yeah? By common cause noise. The other thing is actually you have here the thing of weighting. For example, here my circuit knows actually there is nothing here, and only here the first data comes. Yeah? So I have a notion of no data and data in this circuit. Yeah? And this is quite nice actually if you think about it for genetic circuits, because you don't want your genetic circuits perhaps to always produce something, and they will be very noisy. Yeah? So there is two good reasons actually to, in some places, to use this kind of encoding. Yeah. So this is something that could be, for example, a takeaway from these robust circuits. And and this brings us to our application. You can completely use actually both. Yeah. If you really like both disciplines, I mean, why not use both? And here's an example like this. We presented this in a paper with colleagues. Where we have any gate, like here's an AND gate, but it can be anything, that has dual rail inputs, dual rail output. And since these dual rails, since the signal of the output, for example, here this is the 0 rail and this is the 1 rail, this will be perhaps not perfect, this will be a bit noisy, like it will look like this, right? And this will be a bit higher, let's say. So the real answer is 0 here, but this is a bit a noisy one. You can totally use, for example, now the majority consensus, the algorithm that we saw before, to separate them apart, to determine the majority between this type of species and this type of species. Yeah? So if you run that, ideally that would give you something like this here, right? You can amplify kind of the difference again back. So how would you do that? And one idea we came up is actually, well, the algorithmic rule was that, like, right, it was A plus B goes to empty. And why not say there is like kind of 0 bacteria and 1 bacteria, and they have to only, let's say here in this case, the majority 0 bacteria should survive, right? Because the output would be 0. The problem is only that we cannot only use this rule, yeah? And it would be also not a very good idea because we don't want to be left with 2 bacteria who have the right answer, right? We always have this rule and this rule. That means we always have duplication in bacteria. And we want that actually because we want to amplify up again, the final result. And that makes, unfortunately, analysis a little bit harder. But we can first do some simulation. Yeah, perhaps just a few words before we do some simulations. A few words. How to implement this is clear, right? This is just doing nothing. It's just doing the bacteria. It's a very simple growth model, of course. Yeah, I mean, it's exponential till forever. But let's stay simple for the moment. And how to implement this in bacteria? Yeah, and that will be also problem 3 or 4 in the problem session. So you will take your take on that. But the hint here is actually it can be nicely, or one idea to do that is with conjugation, with something that is called bacterial conjugation, and you can check that out in the problem session. Okay, so let's run some simulations in this very simple model. So this is just some code that you can look through later. And since we're lazy, what you see here, we first tried with just that deterministic, purely simple MobSpy simulations, yeah? So nothing fancy, yeah? And you can see here, it's doing something, yeah? So why not, yeah? Sounds quite right? It's doing a bit the job of going down like before and then growing back, yeah? Sounds okay, yeah? But let's go a bit playing around with that. And what we did is here, we just changed something like with a crazily small number difference between these two initializations. Yeah? And one gives us this one, yeah? And one gives us this one. Yeah? So, I mean, that's a bit puzzling. I mean, of course, we cannot trust the 10 to the minus 11 because this is out of range of the model. Yeah? But still, it's super, super sensitive to super small differences. Yeah? So perhaps it was not a very good idea to run deterministic simulations, yeah, in such a stochastic system. And indeed, if you compare, for example, this deterministic to a stochastic, you see it's doing kind of a different thing. So you should be really careful. Yeah. So it's perhaps better. It's a better idea, let's say, to really think of it as a stochastic system, and to simulate and to analyze it as a stochastic system and not as an ODE. Yeah. So this is one point. I think we had last time the general hint that once you have big counts, you can actually use ODEs most of the time. That would be, this is why it's an advanced course, like this is an example where this is not really the case. You might have very large initial values, but still you really better here use stochastic. And if you do stochastics, this is actually a very interesting curve from it. And I'm going to explain this in a second. 100%, we were purely lucky. It was not it was just a luck. I actually don't. Actually, yeah, here the right one won. Yeah, we were super lucky. Yeah. No, it was a 50-50 chance, right? It's a completely good observation. Yeah. Yeah. So, extremely nice question, because I just wanted to introduce this question. So thanks a lot for this. Yeah, the first thing that you observed here and that you pointed out is something very important. Like I showed you before, in the performance system, we were 100% sure that the difference stays the same, right? And it's always the majority who wins. Yeah? But once we have added A can duplicate and B can duplicate, that's not at all anymore the case here. And the reason is because they can grow back, and like it's a chance now, right? So we don't have 100% or probability 1, or actually for all like always winning anymore, yeah. But we have a probability suddenly, completely, yeah. And this is the graph that I showed you here. This is exactly the probability graph, yeah. So on the x-axis, so it's plotted. Let me check for which total number n it is plotted here. I don't recall. Yeah, so we are sweeping here the ratios. Yeah, with a total of 100. Yeah, so the total population size is 100. And here's the fraction of those being A. Yeah, so this is 100 being A and this is 0 being A. And this is the probability, or here it's actually a fraction because we are doing repeated experiments, yeah, of A winning. Yeah, and as you see, like completely as expected, if we initialize it with 50-50, it's purely chance who wins. It has to, because of purely symmetry, right? If we initialize with 0 or with 100, it has to with 100% probability. But how it looks in between is completely unclear. It's a very non-trivial question. It's a very difficult question, and it looks like that. I mean, this is not a mathematical proof. Yeah, this is like our second stage of simulation. Like we are using the CRN world to not go to physics. Yeah, so we're speeding up simulation a lot, but we're not doing math here yet. Yeah.
And just went to the stochastic simulation to not be so sensitive about all differences.
Yeah, so there's actually two reasons. Yeah, I would say first, like whenever you see that you are so sensitive, you should really check like if perhaps it's not a bad idea to go stochastic. Yeah, but the second thing is like this question cannot at all be even answered in the deterministic way, right? So you could not produce, for example, this curve here, because I mean it's if it's an epsilon under and you don't have numeric integration problems, it will always win. Yeah. So.
Problem.
Okay, the question is like, what do you want to do completely? Yeah. So in the, let's say in the original thing when you can choose completely your system, then you should have not chosen. You should have just chosen, let's say, this rule, right? And you should have taken that rule because that's 100% doing the right job. But what I'm saying is like, when we try to implement this in bacteria, we have to buy 2 other rules. Yeah, it's not a choice. We have to, unless if you tell me to make this bacteria do this job, but completely inhibit them to duplicate, which is perhaps even not a very good idea because then they just start dying slowly and you lose your signal perhaps. So we kind of have to buy this. And then we are in this domain of having these difficulties. Yeah. But thanks a lot for these questions. Yeah. So this is a purely simulational, and I mean it looks like a steep line here, right? So let's zoom in if it's so steep. And this is just the same code, just doing more repetitions in the middle. Yeah, and this is now not fractions. This is absolutely differences for 1000. Yeah. So here we have 500 minus 5 plus 5, so a gap of minus. Wait, no, it's a minus b, exactly. Sorry, it's a minus b here, actually, minus 10 and here 10. And you see, like, if your gap is already 10 of 1000, which is really a small percentage, I mean 1%, then it's a clear win for B, and here it's a clear win for A. So it's very, very sensitive, right? Okay, and the question is like, I mean, it's amazingly sensitive, but can we say something? And before we say something, and that brings me like perhaps I will perhaps use 2 more minutes. I want to present another thing. We had this rule, right? So that we started with this algorithm, right? But this is not so trivial, as you will see in the problem session. This is not so trivial to build in bacteria. Yeah, you will really think of conjugation, and it's not trivial. It's really a hard job to do that in bacteria. Like, it would have been much, much simpler if we could have a rule where we don't interact, but we just do something. Yeah. For example, you could think of, let's have a much simpler system. Let's have just something where A and B independently die. Yeah. Or they are eating a common resource here. This can be a common thing even, yeah. So you're controlling things from a common resource. But wait, just connect again. Yeah. So you can go wild here, but you're not allowed to interact with B and A. Yeah. So these are much more easy to implement. I mean, this is actually for free, right? In a bacteria, they die and they duplicate. Would this system also amplify so nicely? And amplification, we mean like curves of here's the fraction, here's the win probability, doing this S-shaped curve, like a very steep amplification around the 50-50 point. And the answer is no. Like, they don't do that. They do essentially this. It's a purely linear, like non-amplified system at all. And there's a very nice symmetry argument. Essentially, you can also say you can view each bacteria as a purely symmetrical system to the others. And there is no advantage of any single A over any single B. So it will be always just A divided by A plus B, right? This line. It will be purely, how many more A's are in the system than there is B's, essentially. This is the probability that they win. Nothing. They cannot amplify this difference. And that's a very interesting design rule for us, right? Like it tells us if we want to design amplification, we have to use actually interaction. In this play of games. And okay, I don't have the time actually to go through the theoretical analysis, but we have a bit modified the analysis from the last week. So if you read this last week, we tried to make it really much more nice reading now, much more digestible, much more light. And we think we achieved at a quite nice digestible level. So if you want to give it a read, give it a read. Again, this is an advanced topic, so you don't need to, but it might be fun to see that you actually very surprisingly can say something extremely precise about this curve here. It's a very well-known precise curve. You will not have exactly the curve, but this is a very, very nice bound, yeah, that is well known. And for those interested in mathematics, I mean, this is very closely related to an UN problem. Hope I'm pronouncing it correctly. UN problem. Yeah. So it's polar urns, and yeah, just give it a read and have fun. Yeah. And I think this brings me to the yeah. This is actually how that looks like if we plot the bound there. Yeah. So the bound gives us really some nice S-shape here. Yeah, and that finishes the third part of the lecture. Hope you enjoyed it. Hope you had fun. Yeah. And if you have any questions, feel free to ask them. Yeah. And if not, like let's start the problem session. Problem session will be, they will have some introductory math things. Yeah? We start with a kind of a warm-up because it's a problem that you already solved in the previous lecture, but we want you to find a very simple symmetric argument, because like we think that sometimes symmetric arguments, like here you saw that they are super strong sometimes and give you very immediate proofs, and yeah, it would be just fun to find a simple proof. And the last problem will be actually the most probably time consuming, and you will try to design plus meets for this AB algorithm, right? For the pairwise annihilation. Okay, thanks, and see you after the problem session.